Some aircraft earn their legend through speed, others through mystery, but this one earned its legend through survival. The A-10 Warthog wasn't built to be pretty or fast. It was built to bring its pilots home. With wings wide and strong enough to lift a flying cannon into war, it became a machine soldiers learned to trust more than luck itself. It flies low, it flies slow, but for over 50 years it's never failed the troops beneath its shadow. In the late 1960s and early 1970s, the U.S. Air Force knew that its supersonic fighters like the F-4 Phantom II were not suited for close air support. They were too fragile and too expensive to loiter over battlefields. Ground troops needed something different. They needed a flying tank that could circle overhead for hours and strike with devastating accuracy. This is where the AX program comes in, a competition to build a close air support aircraft. Fairchild Republic's design won. Its philosophy was radically different from most modern fighters. Instead of swept wings meant for supersonic speed, the A-10 featured long and straight wings optimized for stability and maneuverability at low altitudes. These wings gave the A-10 the ability to fly slowly over battlefields and bank sharply at low speed. The Air Force was buying a promise that its wings would always be there above the battlefield when soldiers called for help. The A-10's wingspan measured 57 feet and 6 inches, with a large surface area that produces enormous lift at low speeds. Unlike swept-wing fighters, the Warthog's straight wing generates stability instead of drag during slow flight. This allows the aircraft to fly at speeds as low as 300 knots, or even lower when circling tightly over a target area. Those wings give the A-10 superb short takeoff and landing ability. It can operate from rough airstrips, damaged runways, or even makeshift forward bases close to combat zones. For troops on the ground, that meant the Warthog didn't need pristine infrastructure to come to their aid. The shape also allowed heavy payloads to be slung under 11 hardpoints. Missiles, bombs, rockets, and even fuel tanks could be spread across the wing without destabilizing the aircraft. And at the centerline, the wing supported the A-10's defining weapon, the GAU-8 Avenger cannon. If you like this video so far, make sure you like it and subscribe to the channel. And let us know in the comments, which mission do you believe shows off the A-10's wings best? The A-10 became famous for its ability to take damage and keep flying. Its wings were central to this reputation. Unlike fragile, high-performance jets, the Warthog's wings were built thick and tough by using structures that could be repaired very easily. Fuel tanks inside the wings were self-sealing and were able to close up after being punctured by enemy fire. But what's even more remarkable is that the aircraft could still fly with half a wing blown apart. There are countless combat stories of A-10s returning home, riddled with bullet holes with its wings shredded, yet still able to carry pilots safely back. The placement of the engines also played into survivability. By mounting them high on the fuselage and shielding them with the tail, the wings remained free to carry armament and absorb damage without losing any thrust. It was a system designed not to avoid danger, but to fight through it. If the A-10 is famous for anything, it is the 30mm GAU-8A Avenger cannon. This 7-barreled rotary gun fires nearly 4,000 rounds per minute, powerful enough to tear through armored columns. But how is this relevant to the wings of the Warthog, you might be thinking? To mount such a weapon, the entire aircraft had to be rethought. The wings were surely surfaces for lift, but they also became structural partners in the gun's integration. Because of the cannon's size and recoil, engineers shifted the landing gear into pods on the wings, freeing space in the fuselage and keeping the aircraft balanced when firing. The wings also had to absorb and distribute some of the recoil forces, ensuring stability during long strafing runs. Beyond the cannon, the wings carry most of the A-10's firepower. Out of 11 weapon stations, 8 sit under the wings, each reinforced to carry missiles, bombs, or external fuel. This flexibility turned the wings into the backbone of the Warthog's entire combat system that was capable of adapting Cold War tank hunting and precision strikes in modern conflicts. And it could do all this without changing their essential design. Before we move forward, there's a question we want to ask you. Do you think the A-10's straight wings are the real reason it can fire the massive GAU-8 cannon so accurately? Or would it have been just as deadly with swept-back fighter wings? Let us know what you think in the comments, and we'll get back to this at the end of the video. One of the A-10's greatest strengths was its simplicity. While stealth aircraft like the B-2 or F-35 require specialized hangars and complex coatings, the A-10 was built to be maintained in the field. Its wings used traditional aluminum alloys and accessible paneling. Ground crews could replace sections quickly without advanced equipment. This was no accident. Designers anticipated a European battlefield where runways and depots might be bombed. The A-10 needed to be cheap to fix and easy to fly again. Its wings were bolted and riveted with this philosophy in mind. Even battle damage could often be patched up in days rather than weeks. This repairability extended the jet's lifespan. While many 1970s aircraft have been retired, the A-10's wings have been kept in service through careful upgrades and replacements. The wings of the A-10 were built for staying power. By producing high lift at low speed, they allowed the aircraft to loiter over battlefields for hours. It has a combat radius of nearly 300 miles on internal fuel that is extended by drop tanks under the wings. This means that the Warthog could provide support without needing constant refueling. But why was this necessary? This endurance was actually critical for close air support. Ground troops could call in the A-10 and know it would stay overhead long enough to eliminate threats, wait out ambushes, and then also deliver repeated strikes. Where supersonic fighters often had to leave quickly to refuel, the A-10's wings kept it present where it mattered most. The loiter capability also tied directly into its slow, stable flight profile. By circling at low altitudes supported by those wide wings, the A-10 could aim its cannon and weapons with precision unmatched by faster jets. The A-10 was never meant to last into the 21st century, yet its wings have kept it alive. By the 2000s, fatigue began to threaten the fleet, with cracks and wear appearing after decades of combat service. Retiring the aircraft was considered, but instead, the Air Force invested in a massive re-winging program. New wing sets were produced with modern materials and design refinements. This program was completed in 2019 and gave the A-10 fleet decades of additional life. The aircraft now has wings strong enough to serve well into the 2030s, even as debates continue over whether it should finally be replaced. The A-10 Warthog's wings symbolize a philosophy that feels almost alien in today's age of stealth and drones. They are broad and visible, unapologetic in their own way. Unlike other aircraft, they don't hide, they endure. And in enduring, they've proven themselves across conflicts from the Gulf War to Afghanistan and beyond. While critics argue the A-10 should be retired in favor of multi-role jets like the F-35, supporters point to those wings and their unmatched capabilities. No aircraft has yet combined the same slow-speed agility, loiter time, payload, and survivability. For soldiers on the ground, the Warthog's wings are more than aluminum and rivets. They are constant reassurance that circles above with the unmistakable growl of the GAU-8. Whether the A-10 remains for another decade or finally leaves the skies, its wings will remain a symbol of battlefield presence and trust between air crews and troops. They are proof that sometimes the simplest wings make the most lasting mark. To get back to the question we asked before about how much the wings really matter when it comes to the Warthog's firepower, the truth is, without those straight, broad wings, the A-10 could never have fired its cannon with such stability. Swept-back fighter wings are great for speed, but they don't provide the slow-speed lift or balance the Warthog needs for repeated strafing runs. It's heavier than a tank, bigger than a train car, and it's powerful enough to launch a fully loaded Boeing 777 into the sky for 15 hours non-stop. This isn't the work of any engine, it's the GE-90. The largest and most powerful jet engine ever put on a passenger plane. And inside this giant monster are parts so delicate that a microscopic crack could bring it all down. The GE-90 redefined long-haul flight when it first launched in 1995 with over 127,900 pounds of thrust and fan blades taller than an adult. Before it came along, transoceanic travel depended on four-engine giants like the 747. But the GE-90 made it possible for a twin-engine jet to fly routes beyond the Atlantic and the Pacific. This changed how airlines operated forever. The 777 became the backbone of long-haul fleets, and the GE-90 was the muscle that made it possible. But raw power wasn't going to cut it alone. Every inch of this engine had to be carefully designed because if even one part failed, the entire system could collapse. The front of the GE-90 is impossible to miss. At over 128 inches across, it is wider than the fuselage of a Boeing 737. And yet it only has 22 blades. Compare that to older engines which had more than 40 or 50. But why design the engine to have fewer fans? Because these blades are bigger, lighter, and far more efficient. Each blade is made of carbon fiber composite with a titanium leading edge. They're built using a process called resin transfer molding, then cured in autoclaves so large they could fit a bus inside. The shape isn't random either. They're curved into a distinctive scimitar design to not only grab more air but also reduce noise. This is one reason the 777 is quieter than older jets despite being much larger. And the wild part is that those blade tips travel at close to 1,000 miles per hour, just under the speed of sound. During testing, GE literally fired frozen turkeys into them to simulate bird strikes. The blades survived. Each blade costs more than a luxury car, and when you line up all 22 of them, they form the hypnotic spinning disc that feeds the rest of the engine. But once the air is pulled inside, things get even more extreme. Behind the fan lies the compressor, which takes air at normal pressure and squeezes it until it's 40 times denser. Imagine crushing a room full of air into a shoebox, and that's basically what's happening here. The GE90's compressor has 3 stages of low-pressure compression, followed by 10 stages of high-pressure compression. Each stage has blades shaped slightly differently and tuned to gradually build pressure without stalling the flow. The engine uses variable stator vanes that pivot in real time to optimize airflow at every speed and altitude. Over 1,200 kilograms of air per second rushes through the GE90. Each of the compressor blades is forged from nickel superalloys and inspected for cracks invisible to the human eye. Because even one blade failing under the enormous stress would have catastrophic effects. Before we move forward, here's a question for you. Why do you think the GE90's compressor uses concentric shafts that spin at different speeds instead of a single shaft for all stages? Let us know your guesses in the comments below, and we'll get back to it at the end of the video. The combustor is where air and fuel meet. It's an annular combustor in the shape of a ring, where 30 fuel nozzles spray atomized jet fuel into the compressed air. A tiny spark sets off a fireball at over 2,000 degrees Celsius, which is hot enough to melt most metals in seconds. So how does it survive? With film cooling where thousands of microscopic holes line the walls of the combustor, a thin sheet of cooler air flows across the metal and creates a protective shield against the inferno inside. At its core, the flame burns at nearly 2,500 degrees Celsius, but by the time it reaches the turbines, it's cooled to about 1,500 degrees Celsius. That's still hotter than the melting point of steel. The turbines sit just behind the combustor and harvest energy from the rushing exhaust gases. They spin at over 10,000 revolutions per minute and glow red hot from the heat. But these blades aren't ordinary metal. Each one is grown from a single crystal of nickel alloy. No grain boundaries, no weak points. It's a material science breakthrough that allows them to survive temperatures and forces that would destroy almost anything else. They're hollow with air channels running through them to keep them cool. And they're coated in ceramic layers to withstand heat above 1,600 degrees Celsius. Even more impressive is that they're designed to twist slightly under stress, so they only reach their perfect aerodynamic shape when they're running in actual flight conditions. The design is genius. It's a blade that isn't perfect until it's on fire at 30,000 feet. Heat is the GE90's greatest enemy, and cooling is its hidden weapon. Inside, air is bled from the compressor and channeled into microscopic passages to stop the turbines and combustor from melting. The materials are chosen with precision: titanium in the fan and front sections for strength and weight savings, carbon fiber composites for the giant blades, nickel alloys and ceramics for the hot turbines. Even the bolts are matched to expand at the same rate as the metal they hold, so nothing cracks under stress. This quiet war against heat is what allows the GE90 to run for thousands of hours without failure. An engine this massive can't rely entirely on metal and fire. In fact, it has a brain. The GE90 is fully managed by Full Authority Digital Engine Control, or FADEC. Think of it as the autopilot for the engine itself. Instead of pilots manually adjusting throttle settings like in older jets, FADEC constantly monitors thousands of parameters every second, for things like fuel flow and temperatures, and makes micro adjustments faster than any human ever could. The result? Maximum thrust when you need it, and safer shutdowns if something goes wrong. It also means that every GE90 performs identically, no matter which 777 it's on. Airlines get consistency, passengers get reliability, and engineers get endless streams of data to predict issues before they happen. If you're enjoying the video so far, don't forget to like and subscribe to the channel. And let us know in the comments what you find most fascinating about the GE90. We love hearing your thoughts. At GE's massive assembly plants, the GE90 comes together piece by piece. Cranes move modules the size of trucks into position. The engine is built in sections: fan, compressor, combustor, turbines. Each module is tested individually before being joined to the whole. By the end, the engine stretches more than 24 feet long, weighs over 8 tons, and contains more moving parts than a Swiss watch. Only this watch doesn't tell time. It hurls a 300-ton plane across oceans. Then the GE90 undergoes rigorous testing. Engines like the GE90 are tortured before they ever see a plane. They're chained down and blasted at full power in test cells the size of hangars. The noise reaches over 140 decibels. For reference, that's louder than a rock concert. Massive underground ducts are used to absorb the roar so entire neighborhoods don't shake. Engineers simulate hail, freezing rain, sandstorms, even volcanic ash. They shoot birds and ice blocks into the fan. In one legendary test, GE deliberately broke a fan blade while the engine was at maximum thrust just to see what would happen. The engine tore itself apart, but the debris stayed inside exactly as designed. Safety is never optional in aviation. The GE90 was about brute force and efficiency both. Its high bypass ratio meant that most air flowed around the core instead of through it. This makes it quieter and more fuel efficient. Its specific fuel consumption sits at around 0.52 pounds of fuel per pound of thrust per hour, and that's remarkable for an engine of this size. Later, upgrades brought 3D printed fuel nozzles, lighter materials, and advanced sensors that beam real-time performance data to airlines mid-flight. And then came the next chapter, the GE9X for the 777X. Even larger, even lighter, with fan blades so thin they look impossible. It's already shaping the future of long-haul travel. The GE90 is proof of what humans can achieve when they push engineering to the edge. It reminds us how every leap in technology changes the way we travel and connect. And about that question from earlier. The GE90 uses 2 concentric shafts, so each compressor spins at its optimal speed, the low pressure slower, the high pressure faster, maximizing efficiency and preventing instability. If you enjoyed this deep dive into one of aviation's greatest machines, hit like and subscribe. Because the next story we uncover might be even bigger.